it's not clear that connected communication can help with, although there are people working on, for example, high-speed turn alerts for cars, so maybe some of that could apply. It's possible even that crowdsourcing bike routes, people could find safer routes to ride on. But generally, that's going to be a pretty tough problem for some sort of piece of hardware that you put on your bike to help. The second cause is motorists themselves. So big change in kinetic energy if a large vehicle actually runs into you. And then the third is, of course, the cyclist. And as we know, cyclists often sometimes act like pedestrians, sometimes they act like cars, and so it can be a little bit in their hands as well sometimes. If you look at most of the serious injuries and fatalities that happen, almost 90% of them, the ones where cyclists actually end up in the hospital, come from getting hit by motorists. And so for most cyclists, this probably isn't a big surprise, but it basically tells you that, if a cyclist crashes due to a road problem, or they hit a patch of ice, or crash into a pedestrian, these aren't the types of injuries that are really necessarily fatal or serious. It's really the crashes with cars. And so we've been looking at this sort of how can technology help, and this is a kind of a funny ad from the 70s that I believe is from Ford. And if you can't read the title at the bottom, it says, "The rear of this wagon is a play area." So you've got a whole bunch of kids that are kind of hanging out in the back. This, by modern standards, seems pretty absurd. I would argue that in the coming years, in the next 5 to 10 years, as autonomy and connectivity and sensing in vehicles and bikes and pedestrians becomes more commonplace, we'll look back at our current road system and kind of laugh at it in the same way that, hey, wow, these cars were driving and they didn't have radio beacons talking to each other. So what is the real key problem? Why do cars actually crash into bikes? And it tends to come back to this notion of what's called perceptual blindness. And so I don't know if you guys have seen this video from a couple of years ago where it was a psychology experiment where they actually asked people to count the number of basketball bounces of a team that was kind of moving basketballs around in a room, and people would watch the video, they'd count, and they might actually be really close to the right number. What they wouldn't notice is that in the middle of the video, there was a guy wearing a gorilla suit that just walks through the center, stands, kind of beats on his chest. Something that normally you would assume that you would notice, but because of this perceptual blindness, because you're focusing on other things, your brain is basically trained to do that instead, you ignore some of the peripheral information. And actually, more recently, if you want to check it out, they have an updated version of this where the ball is bouncing around, you're counting the ball, the gorilla comes out, everybody expects it, so they see the gorilla, and they say, okay, yeah, I saw the gorilla, and they don't realize that the background of the scene is changing colors, windows are appearing, window shades are coming up and down, and so it just shows that even when you know you're going to get tricked, it's tough. And so when it comes to drivers are really trained on the road, they're trained on traffic lights, they're not seeing cyclists. So one of the challenges that we've been faced with is, okay, well, maybe we can alert drivers of cyclists, and particularly maybe we can actually filter based on different situations that are occurring. So we've been looking at sort of technology for that. The second problem, of course, is reaction time. So sometimes a driver will see a cyclist, particularly at night. A lot of cyclists have blinking lights. They're actually highly visible. We were kind of surprised to find out that most accidents happen during daylight for cyclists, not at night. And the issue here is that, as humans, we actually don't have necessarily the best reaction time. And so if there are ways of predicting and alerting that are faster than human reaction time, this would, of course, help in these types of situations. So I'm going to start off by talking about connected technologies. I'm going to give a little bit of an overview of what's called DSRC. And then I'm going to talk specifically about some of the work that we've done on biking hardware. And I actually brought a little bit of a prototype system that you guys can feel free to come up and look at after the talk. And at the end, depending on how much time we have, I'll talk a little bit about some of the stuff that's been going on in autonomous vehicles on campus, if you're interested. So what is DSRC? So DSRC is short for Dedicated Short-Range Communication. The idea is it's a dedicated communication channel. So unlike the wireless that you have in your house, which is considered shared spectrum, Dedicated spectrum basically means that nobody else is allowed to transmit on that particular frequency. So there's essentially a government regulation that says, okay, there's a slice of communication, wireless communication that we can use that nobody else is allowed to use, and it's dedicated specifically for communication between vehicles. And so the idea is that all of the different cars / traffic lights in the future will have these radios. They'll be able to communicate with each other to exchange information. And kind of over the next couple of slides, I'll talk about some of the different benefits that people envision for that. But the high-level idea is that you have essentially what looks like a Wi-Fi access point in your car. It'll look a lot like this thing on the front of the box that's really custom-built and specific for traffic and vehicles. So there's sort of two general types of DSRC communication. So one is called V2I, or vehicle-to-infrastructure communication. This would be that your car, your bike, your pedestrian, whatever it is moving around in a city, is able to talk to things like traffic lights. So one question might come up, why do we care about talking to traffic lights? Well, you can get information from them about, for example, the map of the intersection. You can get map information. You can see the geometry of the road. You can also find out about light timing. So if a light is about to turn red and your car basically detects that you're going too fast, you're not going to be able to stop, it can warn you. You can even use it as a connection potentially to the internet. So if you want to get updated information about traffic, a lot of that can come from the infrastructure side of the system. So V2I is kind of a really interesting component to the system. V2V, which is vehicle to vehicle, that's the form of communication where the cars are talking to each other. So the cars exchange information about, am I braking really fast? Am I about to crash into the back of another car? Can the car automatically stop? Can it tell me that I should be slowing down? All of these types of things. Does it detect that there's a mechanical failure in the car in front of me? So you can imagine lots of these reasons for doing alerting from vehicle to vehicle. In these cases, the challenge is really making sure that the connection is very low latency, right? You're talking about cars that are moving at 60 miles an hour or plus, depending on the drivers. And they, of course, are potentially coming in opposite directions or coming into intersections or following each other on highways. So you need to be able to establish a connection very quickly. Security also becomes a very important issue here. What happens if somebody tries to hack into the car system, send spurious messages? We need to be able to kind of at least be able to detect those types of attacks. So turns out that DSRC is not extremely new. So the idea has been kind of around since the late 90s. So in 1999, the FCC actually allocated the spectrum. It's been used for toll collection in Europe since as early as early 2000s. So they have kind of their version of Easy Pass, which uses a form of DSRC. In 2004, there was a task group that was formed to really specify how the radio communication should work. And you see here listed this 802.11p. So if you're on campus right now, you're using Wi-Fi, you're most likely using 802.11n. 802.11p is very, very similar to the Wi-Fi technology that you use in your computer, except that it's slightly customized for cars. And the reason why it's important to keep it similar is because think of the literally tens of millions of chipsets that you have for cell phones and laptops. You want to be able to reuse a lot of that in the automotive domain. So they tried to keep it as similar as they could while figuring out these timing and security problems. Then let's see, 2005 through 2009, people worked on a whole bunch of drafts. Turns out it's not simple to come to a consensus. So it took many, many years of people arguing back and forth about the requirements, the features they wanted in the system. And as of recently, NHTSA has basically decided that they will be mandating these transceivers to actually be in vehicles in the United States. And it's kind of estimated that adoption could start as soon as 2017. So there really is kind of the handwriting on the wall saying that this technology will eventually become adopted. So starting in 2014, 2015, ITS DOT has been doing pilot projects in the different places you see on the map, trying to sort of figure out what are the benefits and what are some of the potential problems that could come up with these types of deployments. And we're actually, as I'll talk about a little bit later, CMU in the Pittsburgh area has been doing a lot of this sort of field work and installing some of these DSRC radios. So what do they look like? Well, here's kind of two examples, one of the onboard unit and one of the roadside unit. So the roadside units, if you go down Baum Boulevard, you'll actually see some of these mounted now. There's also a fairly large deployment in Cranberry, but you basically have what looks like a wireless access point that's mounted up on the telephone poles. And this is, of course, the infrastructure section. So these could potentially have a connection back to the internet. So if your car wanted to get updated traffic information, it could. Or they might actually just be autonomous and push out map information locally. The onboard unit, then, is the device that you would install in the car. And of course, all of the current cars, this would need to be an aftermarket device. And so there's kind of a big aftermarket emerging for this technology. But you basically get one of these little boxes that would have the DSRC radio in it, a small computer, a GPS unit so that you can get extra information about where the car is and how it's moving, and then this onboard diagnostic OBD2 interface. And what that does is that actually gives you information from the car. It tells you, for example, if it's braking, if it's accelerating, how fast it's going. That can be fused together with the GPS to give you a much better picture of how the car is actually moving. So if you look at some of the applications of DSRC, there are a fair number of them, like emergency warning systems for vehicles, cooperative adaptive cruise control, if you're kind of platooning down a highway. Lots of these applications that are very specific to cars. There are also a couple that could actually benefit cyclists as well as pedestrians. So the ones that I kind of highlighted here in red, cooperative forward collision warning, so being able to detect if a car is going to crash into a cyclist, intersection collision avoidance. It turns out that a lot of the accidents with cyclists happen at intersections. And then, of course, in-vehicle signaling. So one of the examples that my students like to talk about is the idea of getting doored when you're riding your bike, right? So if a car pulls over, there's this common phenomena where somebody throws the door open, you don't see it as a cyclist, you crash into the door, it never ends well. So you could imagine with DSRC, the car knows that it had just stopped, so the car can see that the person's opening the door. It could actually signal in advance a warning of saying, hey, there's a car that recently pulled over. Be careful, you're coming up on it. So lots of these types of applications. I don't want to talk too much about the DSRC stack itself, but basically at the bottom you can kind of see that it's this 802.11 layer, and the way that they made it more efficient was largely through software. So there's actually kind of a different protocol stack for how you do safety messaging as compared to the regular kind of TCP/IP communication that you would use for browsing the web on your laptop. The whole security component of it is actually quite complex, and it sort of sits along the side of the protocol stack. But the good news is that it's largely software, which means that it can kind of evolve as the system moves. So when it comes to collision avoidance, if you look at a pretty good human's latency, their response time to if they see something happening and when they can react and actually step on the brake, you see numbers around 250 milliseconds. So it turns out if you look at, say, a Formula One driver, somebody who's got really, really good reaction time where basically it's not their brain, it's just their spine that's processing the information, they might be down around 100 or below 100. So the wave communication stack for monitoring a car and actually communicating data can be as low as 20 milliseconds. That was kind of the target that the DSRC designers were shooting for. They wanted sub 100 milliseconds. It typically performs around 20 milliseconds. So when it comes to latency, response time, the machines will definitely be able to respond much more quickly and consistently than humans would. If you look at some of these scenarios like intersections or blind spots, so here's a case where you might have a car that's driving through an intersection, you've got a light changing, you've got the cyclist who sees that the car is still going, you have another car coming across the intersection, the cyclist is hidden. These are kind of some of the standard scenarios that often don't end well. And in these cases, you can imagine by exchanging information about your trajectory, if you've got this fine-grained localization information, you can actually predict potential accidents that are going to happen. And so one of the challenges there, for any of you that have used GPS on your phone or GPS in your car, it's actually not that good quite yet, right? You get 10-meter range. You get a really big circle about where you're located. And that's probably not enough to even really tell you what lane you're in. So a lot of the research that's been going on as part of TSET has been looking at how do I fuse GPS information with odometry, maybe play some tricks with RF and GPS that allow us to get really high precision trajectory tracking to the point where we can start to do things like model what lane you're in, how fast you're going, if there's a potential collision that's going to happen. So there's also a whole set of non-safety critical applications that we think DSRC can be used for. So I mentioned before traffic updates. There's map sharing. So for example, in the case of cyclists, this could be, hey, these are great roads to ride on for the commute. They tend to not have much traffic. I can quantify how close the cars get to me because now I'm monitoring it. You could imagine even map sharing for cars to say, okay, this is the route that I'm going to take. Let's try to optimize and avoid traffic. There's also diagnosis information, social networking aspects, and then even things like data collection. So you can imagine with DSRC radios and sensors equipped to bikes, you could detect potholes. You could even imagine doing structural monitoring of bridges, detecting landslides, of course, watching out for ice, traction control. So lots of really good potential for this technology. We just need to figure out, what are some of these zero-day applications that can allow people to really get excited about it so that it makes it into the public eye and actually gets out into vehicles as quickly as it can. Okay, so now I'm going to talk a little bit about what we've been doing in the Safe Cyclist project. And I kind of like to start off by saying that this is a picture that shows a little bit of the zeitgeist of what's been going on in cycling, but it turns out that cyclist safety is a pretty hot topic, and you've been seeing a bunch of these Kickstarters, and there was a New York Times article about all the gadgets to boost safety on your bike. So here's a picture of kind of an interesting one. It's an airbag helmet that you can wear around your neck, and basically it detects if you're about to crash and expands and covers your head. There's also things for sort of sport and safety, so a smart helmet that can monitor your pulse and tries to measure information about how you're actually looking at the road. These are Helios bars, so these are actually handlebars that you can put on your bike that have a GPS. They have turn signal lights in them, and they can give you turn-by-turn directions. They can also track your bike if it gets stolen. And then there have been a bunch of people who've worked on different headlight systems. So our thought was we should absolutely engage with this community. We should try to take any of the different devices they have and integrate it with our platform. But we were kind of much more specifically looking at instrumenting the bike, looking at mobility patterns, and also looking at the radio technology. So we had kind of a vision of a platform, and so we called it Psychic, or you could pronounce it Shashik maybe. Name could be changing, we don't know. But the idea was that we would look at all of the type of different instrumentation you could put on a bike, and these are kind of classified in terms of the green ones are ones that are pretty easy that we would definitely put on a bike that might actually already be on a bike. The red ones are things that are really expensive, heavy, power hungry, and we'd like to avoid. And then blue ones are, kind of things that we were sort of on the fence about. So for example, electric motors and bikes, do we want to try to make the bike easier for riders? And so what we've come up with so far is this platform. So this is a picture of the spread out version of this platform I have here. And what you see on it is that we basically have a small embedded computer. So we have a BeagleBone Black. So this is something that has effectively the compute power of something like a modern cell phone. We have an 802.15.4 radio, so we have some local wireless communication. And the reason we want local wireless communication on the bike is so that we can talk to other different peripherals on the bike without having to run wires everywhere. We have this high precision GPS, differential GPS system called the Pixie. And this actually allows us to do extremely high accuracy positioning between two of the devices. So if you have two of these Pixie devices, you can actually see within about 2 centimeters positioning error between 2 points. So the idea is that we're using this for some of the ground truth testing that we're doing where when we're driving cars or bikes near each other, we can actually have some type of reference. We're also using overhead cameras to try to ground truth some of that. The big white box is this DSRC radio. And I'll show some pictures in the upcoming slides. They actually have versions of this that are much smaller, that could actually work for cyclists, and that they would be sleeves that you could put around a cell phone. And then we also have this 9 degree of freedom accelerometer that you mount on the back of the bike, as well as the big GPS antenna, which needs a big heavy kind of metal ground plane for now. We also have small little IMU devices which we can put on different parts of the bike, as well as on the helmet of the rider. And so part of that is understanding the dynamics of how the bike is moving as compared to how the head of the cyclist is moving, to see if we can predict trajectory changes. So one thing is if, for example, a bike is going to turn into oncoming traffic, it would be nice to try to detect hints of that before it actually happens. So here's a picture of the bike we instrumented. Unfortunately, the contrast is not very good, but it's basically a Bianchi road bike that we took. The picture shows the platform on the back. The power actually comes from a battery that slides into the water bottle cage. And then we have the IMU unit that communicates wirelessly. It's battery powered. So one is on the front handlebar stem, so we can detect the rotation of the bike. And then we also have a unit which we've sort of connected into the helmet. And actually in the later versions, it kind of moves into the back of it to monitor head motion of the cyclist. So what do we think this technology can actually do for cycling? So the first is these safe routes. We can also detect hazardous road conditions. There's been some discussion about using heart rate signatures to detect stressful road conditions. So places where we can tell from the bike that they're not putting in much power, but their heart rate increases. There's been a lot of work in this in race car drivers as well as taxi cab drivers across cities to sort of indicate stress. Collision avoidance alerts, which is why we're doing all the differential positioning. And then smart lighting, automatic 911. If you detect, for example, that a biker crashes, you can call for help. Traffic law notifications. So we had this notion of what we call karma. So a lot of times cyclists tend to do things like go through red lights. We like to kind of have a scorecard that says, hey, this was potentially a near miss. You shouldn't do that. And then also video accident logging. So a lot of people now who commute and cycle, they actually wear GoPro cameras on the front and back of their bike. And the reason for this is if they do get hit by cars, they actually want to have some evidence of that. So there's no reason why if we have a sort of smartphone-based system built into the bike, we can't change the optics a little bit to help provide that type of utility for free. So our focus up to this part has really been first and foremost on an app that runs on the smartphone. So what I probably didn't mention when describing the platform is that this is really collecting largely ground truth data and providing the communication plane. Really, our eventual vision is that all of this should be running in the phone, right? So if you have a cell phone that's currently in your pocket, maybe if you can make a mount where you can put it on the handlebars, that's kind of a perfect place to collect data from different sensors. It has the GPS, it has the communication. It's actually very simple to add DSRC to cell phones. And so that really does seem like the sort of future direction for this technology. We also want to look at, if you have that, can we actually accurately do collision warnings, vehicle proximity? And then while we're at it, we have a couple of sort of fun features that we're trying to add to the bike, like turn signals, data logging from the helmet, and even communication to the rider through the rumble bar. So some of the existing technology, so these are all Bluetooth peripherals that connect to our phone interface. So we have a strain gauge on the bike, so you can actually tell how much power you're putting into it, heart rate monitor. We even found that Garmin has an nifty Bluetooth-enabled tire pressure monitor. And so all of this sort of existing technology connects to the phone hub. I won't go into too much detail about this, but we have kind of a software architecture that we're designing to help make it simple to collect this information and then hopefully to actually engage riders to use it. So we're pulling in some components of cycling fitness apps, like basically keeping track of distance, keeping track of routes you're taking, and then at the same time using that as kind of a back channel to log the information about trajectories and to communicate with our data collection box in the back. So one of the trickiest parts about looking at collision avoidance in cyclists is that they often have these kind of three distinct behaviors. So the first is they can actually be riding on the road just like a car, and they have kind of a driver behavior. So this is something that the DSRC community has studied a lot. They've looked at cars, they've looked at how cars change lanes, how they accelerate and brake, and they've kind of modeled that for their collision avoidance systems. So we can take that and almost directly apply it to bikes. The trick is that bikes also have this shoulder riding modality where you're acting kind of like a car, except that you're going to let people pass you, and you're right at the edge of the road, except that you'll dart out occasionally if there's, for example, grates on the street, like what you see in Pittsburgh pretty frequently. And then you have the full-on pedestrian mode of operation, where you may jump up onto the sidewalk. So one of the sort of challenges that we have in understanding when collision warning systems should go off is we have to understand what mode the cyclist is in, and we have to sort of anticipate when these collision warnings make sense or not. The second drivers start to always have some sort of buzzing alert telling them about cyclists approaching them that turns out to not be useful, they're going to very quickly tune that out. And so we've been spending a lot of time trying to figure out how to make those alerts meaningful and detect. So this was actually a picture I was hoping to see earlier. So this is the same company that makes this white DSRC box. They actually developed a holder for a cell phone. So the idea being that you can slide a cell phone into it, and then this acts now as the DSRC modem, plus it actually has a quite accurate GPS unit inside of it that can do positioning as well as the communication. And so the hope is that eventually, we'll spend maybe another year working on a platform like this, but then we can migrate towards the sort of more comprehensive, smaller, lightweight platform when we want to do tests at scale. And then talking to companies like Qualcomm, they tell us that it's actually a pretty simple step to put DSRC radio technology into phones. There's already people that are working on trying to increase GPS accuracy of phones. So we're hoping that eventually it just becomes the normal phone platform. We've also looked at reactive lighting systems. So there have been efforts where people have done, for example, projection on roads in front of bikes or virtual lane markers. We've been focusing more on slightly simpler things like turn signals, being able to actually have cyclists send turn signal information to cars that are coming up behind them. But this is something that with our software architecture and with the hardware we have in place is actually relatively simple to implement. We've also looked at connected helmet technology, so having an inertial measurement unit that's inside of the helmet with the communication package that talks to our unit. The idea behind this is actually largely to filter out cases when we know the cyclist has looked around and actually knows about a car in its proximity. So being able to, for example, not alert a cyclist if there's a bus coming up behind it and it looks back and sees that there's a bus. So we can actually use that as a filtering technique. And we're also looking into if we can use that additional acceleration information to help predict the motion of the bike. We've also had a couple of different alert mechanisms. So the bike that we showed has virtual rumble strips built into it, so you can actually vibrate the handlebars to subtly communicate with the rider. This turns out to be a lot harder than it would seem because bikes tend to vibrate a lot, and also depending on the pattern of vibration you send to the handlebars, sometimes the cyclist may notice, sometimes they may not. One of the most important aspects of this, and this is built into the DSRC standard, is having in-car displays. And so we've been looking at getting some existing Android-based in-car displays that we can put in vehicles and actually send alerts from the bike to the vehicle. Being able to have the car avoid the cyclist, we think is actually much more important than necessarily alerting the cyclist of the car. Okay, so now I want to switch gears a little bit and just talk about some of the autonomous vehicle work that's been going on campus, and just to sort of use this as a motivation for how quickly and how evolved some of this technology has actually become. So this is a picture of BOSS, which hopefully from CMU you guys are well aware of, but this actually won the DARPA Urban Grand Challenge quite a few years ago. It was quite a capable vehicle. One of the sort of downsides to it is that it has all of these different sensors on board, right? So if you look at it, it's clearly not your standard run-of-the-mill car. It was able to sort of navigate in urban terrains, avoid people, and drive in a relatively sophisticated environment, but it has lots of these expensive sensors. If you look at sort of the perception that BOSS had, so here's a video that sort of shows an example of the world according to BOSS. Hard to see because of the lighting. But you can already get kind of this notion that it can detect pedestrians, and the box here is annotating that it's actually detecting the person as a pedestrian. It detects cars, vehicles, understands their vehicles, looks at some of this trajectory information. So already a sign that, you know, if autonomous vehicles were sort of to become commonplace, they would have this notion of distinguishing between cars, bikes, people as it moved. And here's kind of an example of a video that the team put together where they basically used BOSS as a virtual valet. So this is a video where Jared, who was one of the main guys that worked on sort of the sensing system and the software, gets out, presses on his iPhone saying, "Go park the car for me automatically." The car goes off and actually parks in Moorwood's parking garage. And then when he's, you know, done at the end of the day, he can come back and call for the car. So fun things you can do with autonomous cars, but again, these sensors are extremely expensive. They're also, they look a little bit strange. Like, you definitely get a lot of attention if you're driving around in a vehicle like this. But keep in mind, this was all technology that was built for the car back in 2008. So of course, at CMU, they're not just sort of leaving it at that. If you look at the more recent version of the work that's evolved from there. So here's a picture of the latest version of the car, which is a Cadillac SRX, with the team, with John Dolan and Raj and everybody that's been working on the system design. The great thing about this is it no longer looks like a spaceship, right? This actually looks like a normal car. It's very hard to sort of tell the difference between this and an autonomous car if you saw it on the street, other than some of the functionality that it has to offer. And here's a video taken this year of the SRX actually able to navigate around the streets of Capitol Hill in Washington, D.C. And so this is Jared from the earlier video, and now he kind of flips the car into autopilot mode. And this is on normal streets, and is able to let it essentially go completely on its own. So he's not controlling the gas, brake, or the steering anymore. He can basically have an emergency stop to override it, but the car is now kind of able to navigate streets entirely on its own. So really, this technology is progressing. It's a lot further, I think, than a lot of people realize. And you can imagine now that if you take the human out of the loop, talking to cyclists, talking to pedestrians, the car can actually automatically sort of react to it. And if this video is on YouTube, you can actually go ahead and watch it on your own time. I promise you the car doesn't hit anybody otherwise. They would have edited it out, but you can watch the timestamps. It looks pretty good. This is also some work from Honda, where they looked at scenarios specifically with pedestrians carrying cell phones. And they showed a bunch of these sort of use cases where they thought DSRC could prevent accidents in this space. And you can see a lot of the sort of similar ideas behind what we're doing with the cycling project. So here's somebody kind of walking out from a curb, maybe slightly hidden, and all of a sudden you get the in-dash alert that says, hey, there's a person here, warns the driver. I don't have the sound turning on, but there's a kind of a loud sound. And then you can imagine it even feeding back to the phone, although I hope people would just not be looking at their phone when they're trying to cross the street, but who knows. So one of the last things that I want to sort of conclude on is there was a really interesting study done by the League of American Cyclists where they went out to a bunch of social media outlets and they asked people what they thought about autonomous vehicles and connected technology, and basically asked them, hey, do you think if this stuff was pervasive, would driving and walking around on the streets be safer? Would it be not as safe? Would it decrease safety? Or do you not really care? And right now, the results they found are kind of surprising. So most people, the majority of people said they really don't know. They don't have enough information. I guess they're the type of people that want to see it and believe it in real life before they necessarily trust it. There was a good chunk of people that thought that it would increase safety. And then there was actually a fairly large slice of people who actually believed that autonomy and some of this communication could potentially decrease safety. And so I found that kind of interesting. So coming from CMU and seeing some of this technology, I think there's definitely work to be done in the perception of autonomous technology and communication in vehicular systems that we need to work on. So I guess to conclude, I just want to say, DSRC is coming. It's basically been pretty much guaranteed at this point. It's going to have incredible implications in safety, and so we just need to figure out how to harness this the best. The cycling community should really try to get involved with this early on. A lot of the information that's been disseminated about DSRC and safety, very, very little of it actually includes cycling or cyclists, and I think it's kind of an important way to make commuting sustainable in the future. And then some of our near-term technical challenges are really figuring out some of this tracking, low latency communication, and then coming up with really meaningful alert mechanisms for drivers and cyclists. And so I also should mention that this work has been done largely by a mixed team of electrical engineer and computer science people, but if anybody is kind of interested in working on this project, they should definitely contact me. We have lots of different work. We also have faculty ranging from Ali, who's in the art department, so he's looking at some of the social interaction sides of this and how we can reach out and build community, to people like Bruno, who works on control theory and tracking, and then of course my team, which works on sensing communication. So thank you for your time. Love to take any questions. So the question was, do I foresee it coming to a smartphone, or when is it coming to smartphones?
Yeah, what's the status of it? Is it realistic that it will be in there, just like Wi-Fi?
So part of the good news is that 802.11p is so similar to Wi-Fi that so I don't want to say anything that I can't guarantee, but it is extremely likely that it's simply a firmware modification to be able to have the latest generation of chipsets and phones support 802.11p. The difference between 802.11p and 802.11n is mostly in how it manages frequency hopping, but the spectrum is just slightly shifted. The hardware can actually do that already. So there's no reason why, with firmware modifications, the latest generation of cell phones couldn't be running 802.11p. So my guess would be the second infrastructure starts to support it, and the second it starts to roll out into vehicles, you'll actually see these patches for phones that allow you to do that communication. In the meantime, I think some of these sleeves for phones, that's really just for researchers. I can't imagine anybody would go out and invest in a sleeve, unless it was to mount on their dashboard, potentially. So I do think it's coming probably a couple years out still, though.
So I guess this kind of addresses the angle of cost as well as getting a filtering. All these things are out of this point. and retrofitting, one or more cars in a household, and a lot of people want more bikes, and they're also on pedestrians. They're just, I saw your mountain, your setup there, the mountain, and it looks kind of big. If there's any, like whatever the system is that's used for pedestrians, looks like it could be, like, people carry their phones with them wherever they go. And
right.
So if you're one bike, you're on a bike share bike, you're on a 1 foot or whatever, it's, if you just have it in your pocket wherever you go, you don't have to think about it. It's not an additional thing. It's not a mouse you have to transfer over or. So I don't know if you just thought about that or anything.
Yeah, so I'm glad to hear you mention bike share bikes. Because bike share bikes do actually have some of this technology in them already for tracking and locking them down. So we are targeting those types of bikes as kind of some of the first places where we'll roll out at scale. This is still, I mean, granted, it's slightly bigger than the iPhone 6 Plus, but not by much, unfortunately. But we do realize this is kind of a data collection platform, and it was, a lot of the metal and the heavy parts of it are to get it better GPS performance for ground truth. Bike share bikes, I think we could actually build something that really interfaces with standard cell phones. Pedestrians, we haven't been focusing on as much. Largely just because there's already other active research into that space. You saw Honda had the demo. Plus, they're a lot slower, so they're kind of easier to work with than cyclists.
How far do you think the autonomous vehicle technology will be ready for the market?
That's a good question. I'm probably not the best person to ask about that, but I mean, there have been sort of recent news releases that have talked about how some aftermarket technology is already becoming available. Every car manufacturer has a prototype autonomous car now. That's pretty much a given. So I think it's really a matter of cost, but largely legislation. Who's liable when an autonomous car crashes? How much does the human need to be involved in the control of it? I think a lot of these are really more policy decisions. I think the technology is getting close with communication. So some of the problem with sensors is that you could have, for example, bad weather, right? You have a lot of rain or heavy snow. Things like LiDAR start to not work as well. So you do need to have this transition over to humans still. With vehicle-to-vehicle communication and better localization technologies, we might even be able to improve bad weather situations. But I think the biggest hurdle right now is still going to be policy-based. And it's actually a shame because there's no doubt if you look at the statistics of how many people die in car crashes a year, it's actually incredible. A lot of them are pedestrians, in fact. And so having autonomous driving as well as really rich and deep sensing and perception would massively help.
What have been the considerations with regards to location, like for example topography or weather, with these technologies and like how?
So I think a lot of people are really hoping that having cars, pedestrians, and bikes be able to sense the environment and then communicate it will be a great way to record information about the environment. So I had this slide about finding potholes and finding icy roads. That's definitely something that will add a quick value return to a lot of these systems. So we had been talking about, for example, outfitting all of the buses in Pittsburgh with DSRC radios and starting to use them as a way to collect information about bridges or sensors that we put on the side of the road. I think that's actually a pretty easy sell, and you'll see that happening quickly.
Is there another like specialization for location that you intend to have?
Oh, so you mean
Like based on the location of where you're cycling or biking? For example, like San Francisco has a very different.
Yeah, so a lot of this comes back to some of the social networking aspects of it and tracking what other bikers are doing and providing suggestions for bikers. When it comes to the actual collision avoidance system, I don't think we have enough information to really change based on region. I think eventually you could imagine learning that there are even different laws depending on what state you're in about how you should treat right turn on red, things like that. I don't think we're quite there yet. We're still working on sort of the plumbing questions of let's make sure if two cars look like they're going to crash into each other, it does the right thing. But I could see that becoming a topic in the future.
In terms of like location, will there be an international standard in terms of the communication protocol?
Yeah, so that is part of, so the question was, is there going to be an international standard as part of the communication protocol? That is part of what this DSRC and 802.11p task force has been trying to do. So right now, the US and Europe are basically on the same page, and I know in much of Asia, they're using the same technology. There's frequency differences, so the spectrum that you use will change depending on the region, but the underlying communication format and how you actually send out messages will be standardized. That's the hope. And there's really a race right now between the US and Europe to see who's going to get this into cars first. And so a lot of the auto manufacturers, they of course build cars internationally. They want the same hardware to be able to work all over the world. So there's a big incentive from that perspective too.
Costs and implementation. For instance, the Cylab insurance, that's a commercial product. But if you look at the infrastructure parts, for instance, the Wi-Fi routers on the traffic signals, those be funded by the county or the city departments in terms of implementation? Because if you're looking at 2017, that's not that far off.
So these will likely be federal mandates. It would be very hard to convince local municipalities that they need to invest in this infrastructure. Whereas if you look at it from the global perspective federally, and you can say, hey, we're going to save X percentage of lives by installing this technology, then it really does become an easy cost-benefit analysis. There have been lots of people that are working on coming up with other service add-ons that make it easier for people to see that they're getting value add quickly. And that's one of the things a lot of the pilot programs are working on. They're working. Yes, yes. So it'll percolate down that way. Cool. Well, thank you guys.